Started.
Oh, shoot.
So, that was weird.
That's all you do is this way.
Alright, so let's remind ourselves how far we got with the modular arithmetic and then continue from there. So, modular arithmetic. First thing we did is we defined these types of sets z sub n, where n some positive integer. And z sub n was shorthand for all the positive integers up to but not including n. Or it's the first n positive integers. For example, if you see z sub 10, the first n natural numbers. So if you see z sub 10, what is that? That's the first 10 natural numbers, namely 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll always start with 0, and so we won't quite get to the number you expect to be in there. That's what that's shorthand for. Z sub 10, first 10 natural numbers. Z sub n, first n natural numbers. If I said z sub 59, that would be all the numbers from 0 to 58. Make sense?
Yeah.
Okay, that's what that's notation's for. Then we create some definitions for how we're going to add two numbers in the system and how we're going to multiply two numbers in the system. And remember, we ran into a problem here because if I tried to do something like 7 plus 7, what happens?
You get 14.
I go outside the set.
Yeah.
And so we decided our sets are going to have kind of this circular motion to them, kind of like a clock does. We don't have any of those clocks in here. But so we start at 7, and now we're going to add 7. So we add 1, 2, 3, 4, 5, 6, 7. And we get 4. 7 plus 7 is 4. Now, this is mod 10. So 7 plus 7, you know, is 14. Mod it by 10, you get 4. Same thing. So you can think in your head, we're going in circles here if that helps you, or you can just add it and then mod by whatever your number is here. Make sense? So that was our definition. Let A and B be members of some set z sub n. Then A plus B, using our modular arithmetic, is A plus B using our regular arithmetic, and then you mod by n. So 7 plus 7 is 7 plus 7, which is 14, mod 10 is 4. Similarly for multiplication. Any questions on those definitions? Remember those? All right. Then we listed out a bunch of properties these things have. Basically saying they behave a lot like the arithmetic you know and love. So for any three members of the set z sub n where n is at least 2, in other words, z sub n has at least 2 elements in it, what are the first 2 elements I always get?
0 and 1.
0 and 1. So when we say that this n is greater than or equal to 2, we're saying there's at least 0 and 1 in there. So as long as you at least have 0 and 1, you get all these properties for free.
Okay.
You get a bunch of them even if you don't have 0 and 1 in there, but we explicitly talk about 0 and 1 in some of them. That's why we say that. So what do we say? We prove this one directly, but we can prove any of these you want. We prove that addition is associative. We prove that A plus B plus C is the same thing as A plus B plus C. And we prove that we didn't prove this one, we could have, it would have been the same. A times B times C is the same thing as A times B times C. Associativity. We also have commutativity. A plus B is the same thing as B plus A, and A times B is the same thing as B times A. This is piggybacking on the fact that our regular plus and multiplication are associative and commutative. That's how we would prove it. We would use the definitions to get back to our regular arithmetic, use the fact that these are associative and commutative, and then use that to show that these are. And then A plus 0 is always just A. So 0 still acts as our additive identity. A times 1 is just A. So 1 still acts like our multiplicative identity. And then A times 0 is always 0. So multiplying by the additive identity still just gives you the additive identity. Pretty standard properties to show up. And they show up here the same way they show up in regular arithmetic. Make sense? Anything weird with those? Okay. Then we were getting to the point where we wanted to start talking about negative numbers now. And subtraction. Really subtraction. How can we start introducing subtraction to our system? And the way that we're going to introduce subtraction to our system is, we'll define it the way you basically expect. How would you expect the definition for subtraction to be? Just looking at these.
The same. A minus.
Yeah, you would expect A minus our modular arithmetic B to be A minus B mod n.
Are you missing anyone?
Nope. And it turns out that that's going to work. We're going to prove that that's going to work. We need to do two things. We need to check that, first off, a minus b mod n is in our set. We can't do subtraction and get something outside of our set. That's a bad operation, right? So we need to make sure whatever this gives us is in our set. The second thing we need to check is that a minus b is well defined, that there aren't two numbers that satisfy that. I don't want to set up a system where 7 minus 6 is 2 or 9. I want it to be one and only one thing. So we're going to do both those in one proof. So if n is some positive integers and a and b are members of z sub n, so z sub n, this could be something like z sub 10, so a and b could be members in a set like that, then there exists one and only one x in Zn such that a plus x is equal to b. And this b, and this x, is going to be what we mean by b minus a. So if I can prove that there's one and only one x that satisfies this equation, then I can define that x to be what we mean by b minus a. This is one way subtraction is often defined in regular arithmetic. You start out with just addition and multiplication, and we say, what do I mean by b minus a equals x? I mean, that is the unique solution x to this equation, a plus x equals b. Find the unique x that makes this true. That's what we mean by b minus a. Okay. That's one way you could have done it in regular arithmetic. Same exact concept here with modular arithmetic. But we need to prove that there's one and only one x that makes this the case. So we're going to prove that there exists one and only one x in Zn such that a plus x is equal to b, namely b minus a mod n. So I'm going to prove that that special x is, are we doing b minus a?
Yeah.
Sorry, wrong word here. So here's how we're going to do it. B minus a, b minus a. Okay. So just like we're following the same thinking there. So I'm going to prove that b minus a mod n, or this b minus a, this thing, is a solution. And therefore that's going to be our definition for subtraction. All right, so let's prove it. Sorry, there's a 1 right there. This part of the chalkboard's just dead. 1, let n be a positive integer and let a and b be in z sub n. And let x equal b minus a mod n, whatever that happens to be. Now this is b minus a regular arithmetic, so I know this only gives me one number. And then when you mod by n, we only get one number. So x is well defined so far. Okay, so remember, what does mod do? Mod gives you the remainder. So this means that x is the remainder when you take b minus a and you divide it by n. So I'm going to take b minus a and divide it by n and write x as a remainder. So then there must exist some q called the quotient in z such that b minus a, the number we're dividing, is equal to our quotient times n plus our remainder. Going back to our very first theorem of number theory. Given any two numbers, in this case it's b minus a and n, there exists a quotient and a remainder such that this is true, where x is going to be between 0 and the number you're dividing by. You follow me there? So I'm just writing out b minus a divided by n. Gives us a quotient, and we know x is our remainder. Because x is equal to b minus a mod n. While we're explaining, you got it? Okay, so then, solve this equation for x, and what do we get? I just need to move the q times n to the other side. So x is equal to, we still have b minus a, but now we have plus negative q times n. Why negative? Because I moved it to the other side. So that's what x is equal to. And also notice something else. Notice that we know x is in z sub n. How do we know that?
It was given.
It wasn't given.
Oh.
We had to prove it.
Yeah.
We know that x, the remainder, can't be bigger than n. What is z sub n?
Everything's smaller than that.
It's all the positive, it's all the natural numbers up to but not including n. It's all the natural numbers between 0 and n, not including n. And we know that x is, where do we have it? Right here. We know that x is a number between 0 and n.
Yeah.
So x has to be in z sub n.
Yep.
So I know x now is in z sub n, and I have a way of quantifying x. X is b minus a plus negative q times n. Now, I don't really care that this is a negative q. Negative q is still just an integer. right? So x is equal to b minus a plus some integer times n. And we're going to do that leap over and over again. I'm going to stop writing a negative q there. So no. From here on out, if I know that x is equal to, this is separated from the proof, in general, if I know that x is equal to y mod n, I know that this y mod n part can be rewritten as y plus some integer times n. Y mod n can always be written as y plus some integer times n. What did I do over here? I had a minus b mod n. That is the exact same thing as a minus b plus some integer times n. Turns out that integer will always be the negative of the quotient, but we don't really care about what exactly it is. We just care that it's some integer. So we're going to be doing this skip a lot from here on out. I'm going to stop spelling it out for you every time. Anytime I see y mod n, I'm going to replace that with y plus some integer multiple of n. They mean the same thing. Let's do a concrete example, maybe before we continue with that. What is 27 mod 10?
17.
It's just 7. It's just 7. But another way we can always write that is 27 plus, there's going to be some integer times 10 that we can plug in there. So we know this is equal to 7, right? And it's also equal to negative 2 times 10. 27 plus negative 2 times 10. That's another way we can write 7. So we can always write this as this, where we plug in some integer there. It's going to be some integer that makes it true. Start with 27, take away some number of 10s, that gets us to our remainder. So start with some number y, take away some number of n's, that's going to get us to our remainder. Or maybe you add some number of n's if we're doing negative numbers, right? What's negative 27 mod 10? 3. Remember, you want to say it's negative 7, but then add 10. So this is the same thing as negative 27 plus some integer times 10. In this case, what's the integer? 3. Okay, so in general, that's what we're going to be doing. So then I know that x is equal to b minus a plus some integer times n, where k some integer. I know exactly what the integer here is. It's negative of the quotient, but I don't care what the integer is. The point is there is some integer. So x is equal to b minus a plus some integer times n, where k some integer. Then let's do some arithmetic now. What am I trying to prove? I'm trying to prove that a plus x is equal to b. I'm trying to prove that x is a unique solution that makes a plus x equal to b. That's what we're after. So let's figure out what that is. Now that I know what x is, I can figure out a plus x. So a plus x is equal to a plus in our regular sense. Remember, to get from this plus, we do regular and just mod by n. So I'm going to do a plus x regular and then mod by n when it's all said and done. So I'm doing a plus, but what is x? It's b minus a plus kn. So I have a plus x all mod n. Put parentheses there if it's confusing you. You good?
You put parentheses now.
No?
Okay.
Do this whole calculation, then mod it by n when it's
Sorry,
done.
you're putting parentheses on x, but yeah.
Same way we have it here. A plus b is a plus b, in parentheses, mod n. Good? All right, now let's do some canceling. What's a plus negative a? 0. Those two cancel out. So we're left with b plus kn, mod n. With me?
Yeah.
Okay. What is kn mod n? What is 100 mod 10?
0.
N.
What is a remainder when I divide 100 by 10? It's 0. If I have 271 tens and I mod by 10, what's my remainder? 0. 10's always going to go into that evenly. It's going to go in there exactly 271 times. How many times is n going to go into k times n?
K times.
Exactly k times. What's the remainder going to be? 0. So k times n mod n is just going to be 0.
But the b doesn't affect that? The k times n? Wouldn't it switch it up so that might not work with mod n?
Why don't you already
No.
have parentheses there? Why isn't that parentheses about b plus k n?
You can mod each individual piece if you want. That's kind of what associativity says is it kind of doesn't matter what order I mod in. I can add those together and mod it, and then add that on and mod it again.
If your b was like 3 and your k and n added up were multiples of 10, right? That'd make it 13. If k was 1, n was 10.
If k was 1 and n was 10,
B was 3.
and b was 3, that would be 13,
And then
which would be the same as if I just got rid of that and just did 3.
Oh, yeah, okay.
Doesn't change it.
Yeah.
Yeah, you can mod anytime you want along here. It's identical to associativity. This is saying we got to mod the result of adding these first, and that doesn't matter compared to modding the result of these first. So you can mod along the way all you want. Doesn't change anything. Good question. All right, so this is just 0. So we have b plus 0 is?
B.
That was quick. B. All right, now it's b mod n.
B.
How do you know?
Because b is less than n, because it's in the set.
Because b is less than n. So if b is 9 and n is 10, what's 9 mod 10? 9. How many times does 10 go into 9? 0. With a remainder of what? 9. So n can never go into b since b is a number smaller than n. So the remainder is always just going to be b. So what did we just already show? A plus x is equal to b. Awesome. So we proved that if you set x equal to, remember we set x equal to b minus a mod n. If you set x equal to b minus a mod n, then a plus x is equal to b. But maybe there's another solution that makes this equation true. We got to make sure that's not the case. So I need to prove that x is the only solution to this equation. X is the only thing you can plug in such that a plus x is equal to b. There's nothing else you can add to a and still get b. That's what we need to prove.
Okay.
Okay. Assume by way of contradiction that there is something else we could add to a to get b. So assume by way of contradiction that there exists some y and z n such that a plus y is also equal to b, and x and y are two different numbers.
Okay.
Okay. Then a plus x is equal to a plus y. How do I know that? How do I know a plus x is equal to a plus y?
They both equal b.
They both equal b. A plus y equals b, a plus x equals b, therefore a plus x equals a plus y. Okay? Using our definitions, what is a plus x? It's a plus x mod n. What's a plus y? It's a plus y mod n. Right?
Yep.
Now, x mod n is the same thing as x plus some integer multiple of n. What integer? I don't know. But you're either going to keep taking away n's until you just have a remainder, or keep adding n's until you just have a remainder. In this case, it'll be taken away since we know x is positive. But so x mod n is just x plus some integer multiple of n. Y mod n is just y plus some integer multiple of n. Where k1 and k2 are just some integers. We don't know what integers. But there are some integers that make it work. Right? Back to what we were saying up here. Y mod n is just y plus some integer times n. Okay. So, we've got this equation. Now, I'm going to solve for x minus y. So I'm going to bring the y over here and everything else over there. So we got the x minus y, that's right here. I need to move the a to the other side, or subtract a from both sides. The a's just go out, you see that? And so on this side, we're going to have a k2 times n minus a k1 times n. So k2 times n minus k1 times n. You see how we get from here to here? Okay. Over here, just factor out the n. And so I get x minus y is equal to some integer times n. What's that the definition of?
Mod.
Modular, what do we call this? Equivalent mod n. If x minus y is some integer times n, that means n divides x minus y, or in other words, x is equivalent to y mod n. Right? And then your guys' homework problem from last week was to show that x being equivalent to y mod n is identical to x mod n equals y mod n. Those two are logically equivalent. You remember that homework problem? And we also did that homework problem in class as part of the regular lecture. I said I'll do it along the way since it's something we have to use.
You did it over there,
Yes, I did it over there.
yeah. Whatever.
All right, well, that's what we proved. And now, what is x mod n?
X mod n.
What is it? What do we know about that number x?
X.
It's a member of Zn. So what is a member of Zn mod n?
X, write that number.
Just x. I know that x has to be an integer less than n. So when you mod by n, we just get x.
Right.
What's 7 mod 10? It's just 7. The whole thing is a remainder. Because n can't go into x. N doesn't go into x. X is too small to get a single n out of it. So all of x is a remainder, all of y is a remainder. So that gives us that x is equal to y. Contradiction, because we assumed x is not equal to y, we got x is equal to y. Therefore, x is a unique solution. Bit of a mouthful. Kind of a tough one to follow, but once you got it, I think you got it. So we got our negative numbers. Or at least we got subtraction. So now let n be some positive integer, let a and b be members of Zn. Now we can define b minus a to be b minus a mod n. Now it's all well defined. We're all good. Cool. Which is a unique solution to the equation a plus x equal to b. That's everything we just proved. Okay, so now we want to go on to division. And we run into a problem with division. You'll notice what we were just barely trying to do is to say, how do I know when b minus a equals x? That's easy. We just check if a plus x is equal to b. If we knew how to do addition, we can figure out subtraction. That's what we just barely did.
Yeah.
Now, can we do something similar with division?
Probably.
So if I want to talk about b divided by a equal to x, all we need to do is find the x such that a times x is equal to b, right?
Yeah.
What is 10 divided by 2?
5.
5. How do you know that? Because 2 times 5 equals 10. Right? So we got to see if we can do something similar like this.
All right.
Here's a problem we're going to run into. In regular arithmetic, you're used to the fact that if you know a times b is equal to a times c, what do you know?
C and B are equal.
B is equal to c, as long as a wasn't 0.
Yeah.
Right?
Right.
Can we do something similar in our arithmetic? Let's check. So we want to know, is it the case that if a times b is equal to a times c, does this give us that b is equal to c? And the answer is no. And so this is where we're going to run into a big problem. What is 2 times 3 in Z10?
6.
6. What's 2 times 8 in Z10?
16.
Mod 10 is 6. So 2 times 3 is 6, 2 times 8 is 6. So 2 times 3 equals 2 times 8. Oh, cool. So cancel out the 2's on both sides and I get 3 is equal to 8.
Yeah.
Which is false. 3 is very different from 8. Not even close, right?
Of course.
Of course. So it doesn't work. So we're in trouble. So our approach here, in other words, if I were to say, if you were trying to think how should we define division, what would 6 divided by 2 be? Would 6 divided by 2 be 3, or would 6 divided by 2 be 8?
Yeah, I see.
That's the problem we're running into. So in regular arithmetic, when we were trying to do x divided by y, how do we define that? We define that to be x times y's multiplicative inverse, where y inverse is the multiplicative inverse of y, yes. Or in other words, where y inverse is a unique number such that y times y inverse equals 1. In other words, how do I do 10 divided by 2. How do I figure out what that is?
You go 10 over 2.
I do 10 times 2's multiplicative inverse. What's the multiplicative inverse of 2?
1/2.
1/2. And we get 5. 1/2 is the unique number such that when I multiply it by 2, I get 1. Right? That's how we define division in regular arithmetic. And this is why you can't divide by 0, because 0 has no multiplicative inverse. 0 times what equals 1? What's the number I can plug in there to make this true?
Anything.
0 zeros.
Nothing. There's nothing you can plug in there to make it true. In fact, you prove that 0 times anything is always 0. So it's never equal to 1. So 0 does not have a multiplicative inverse. That's why you can't divide by 0. Every other real number has a multiplicative inverse. 0 is the only exception. It's a pretty nice set. With the sets we're talking about, it turns out lots of numbers aren't going to have a multiplicative inverse. So you're only going to be able to divide by some numbers, and you're not going to be able to divide by other numbers. It's only numbers that have a multiplicative inverse that you can divide by. And so we're going to have to come up with some method for determining if they have a multiplicative inverse. Now, I'll give you the dumb way of doing it, and then we'll come up with more intelligent ways of doing it. So, quick definition. The reciprocal of some a and zn is b, provided that a times b is equal to 1. So if I'm looking for the reciprocal of a, I need to find the b such that a times b equals 1. If a has a reciprocal, we call it a invertible. All right, so to get a feel for this, we're going to fill out a multiplication table on Z10. So we're going to write out all the possible products that you can get. Now I didn't put zeros in here because 0 times anything is always 0. So that one's not as interesting. So let's fill out this table. What's 1 times 1? 1 times 2? 3? 4? 5. Hopefully you see this and we're not skipping anything. Good?
How'd you get the 8?
I thought I said A. I thought, wow, I must have written something terrible. Okay. And similarly for this, 1 times 2 is 2, 1 times 3 is 3, 4, 5, 6, 7, 8, 9. Notice so far we found something. 1 times what gave us 1? 1. 1 times 1 gave us 1. So 1 is its own multiplicative inverse. So if you want to divide by 1, that's the same thing as multiplying by its multiplicative inverse, which is 1. And that's also true in regular arithmetic. What's 100 divided by 1? 100. Same thing as 100 multiplied by 1. Because 1 is its own multiplicative inverse. All right, let's do the 2's. 2 times 2 is?
4.
2 times 3 is?
6.
2 times 4 is?
8.
2 times 5 is?
10.
2 times 5 is?
10.
2 times 5 is?
1. 0.
Oh, it's 0.
0. 2 times 6 is?
2.
2 times 7 is?
4.
2 times 8 is?
6.
2 times 9 is?
8.
And also it has a nice pattern. 2, 4, 6, 8, 0, 2, 4, 6, 8.
I see, okay.
If we would have had the 0 on here, we would have had 0 as well. So 0, 2, 4, 6, 8, 0, 2, 4, 6, 8. All right. And it's giving me the same numbers going across here. This is also going to be 6, 8, 0, 2, 4, 6, 8. This symmetry across this line is the same thing as it being commutative. Okay, what's 3 times 3?
9.
What's 3 times 4?
2.
What's 3 times 5?
5.
What's 3 times 6?
8.
8.
Not Jeremy. What's 3 times 7?
1.
1.
What's 3 times 8?
4.
Jeremy wasn't even talking.
Sorry.
That's even who I meant. Ah, can't teach brothers. All right. And the last one is
7.
7. And what's the pattern there?
There isn't one.
We'll just
You were manually doing that each time. You're just counting by 3s.
Oh.
3, 6, 9, 2, 5, 8, 1, 4, 7.
Yes.
Imagine cycling through.
Wow.
All right, let's see if you can count by 3s again. 9 plus 3 is?
1.
2. 2 plus 3 is?
4.
5. Are you messing with me? 5 plus 3 is?
8.
8 plus 3 is?
1.
Plus 3 is?
4.
Plus 3 is?
7.
Wonderful.
What happened to 0?
We didn't put zeros on the tables. Because 0 times anything is always 0.
There's no
Oh,
zero.
shoot.
It's the same thing as when you filled out a timetable in grade school. They didn't give you the 0 row and the 0 column. They made you start with
It
ones.
would have
What
been
I'm
0 after.
thinking is
Like when we're counting.
8 plus 3. Oh,
Oh, 7 plus 3 would have given us 0.
Yeah.
yeah, I was thinking something else.
Okay. Next one. 4 times 4 is
6.
6. 4 times 5 is
0.
0. And then, come on.
4.
And then,
8.
and then,
12.
2.
I mean 2.
and then,
6.
wonderful. Same thing across here. 0, 4, 8, 2, 6. Okay, 5 times 5 is
25.
5. 5 times 6 is,
Hurry my intuition.
0.
and then,
5.
and then,
10.
and then,
Oh, yeah.
come on. 5, 0, 5, 0, 5, 0, 5, 0.
Oh, that.
Get the pattern, people.
Hold on.
Yeah, when you count by 5s in mod 10,
You can't
the remainder's either going to be 5 or 0. 5 or 0. Nice and easy. All right, 6 times 6 is
6.
6.
6. All right, plus 6 is
1.
2.
2.
an even plus an even is even.
Right.
6 plus 6 is 2. Plus 6 is
8.
plus 2 is
4.
4.
or all right, and 2, 8, 4. Wonderful. 7 times 7 is
7. 4.
Whoa. Buddy.
9.
9. 7 times 7 is 9, people. Come on. All right. Plus 7 is
6.
7. 6.
plus 7 is
An odd plus an odd is always an even.
5. I mean
3.
3. Good
4.
job. All right.
That's close.
And then 6 and 3. All right. 8 times 8 is
4.
4. Plus 8 is
6.
12. 2.
2.
Let's go.
4 plus 8 is 12. All right. And then plus 8 again is 2. And then finally 9 times 9 is
1.
all right. We did our multiplication table. Whew. We did it for Z10. Imagine if we had to do this for something like Z561.
We wouldn't.
It's a nightmare.
Oh, is that symmetrical?
Yes, it's symmetric.
Yeah,
That means it's commutative. If your table is symmetric, that means it's commutative. Anyways,
Huh.
Wow.
That's not even true.
yes, because 1 times 3 is the same thing as 3 times 1.
Not only
No,
that,
it's
it's
symmetrical this
symmetric
way.
the other way.
Oh, I meant it's symmetric this way.
Yeah,
Yes.
but it's symmetrical the other way too.
I was
It's
thinking
symmetric the other way too.
Does that mean it's associative?
It's symmetric the other way too.
Yeah,
What do you mean by
like
that?
1, 2, 2,
1, 2,
3,
3,
4,
5, 6,
3.
7, 8,
Those are on the other side.
If you go 9 to 9, it's symmetric, right?
Draw y.
You're saying this and this are same, this and this are same?
Yeah.
That's what I'm saying. Here's your line of symmetry.
No.
If you fold on that line, all the same
Oh,
numbers hit
that's
each
true.
other.
But-
Can't you do the other
But
way?
fold it the other way too. The other corners to the other corners. And it works.
Oh, that's what you mean.
Yeah.
Symmetric
Yeah.
this way. Oh, okay.
Which isn't the case with all commutative ones.
Correct.
So you should draw the line.
Well, I need to use this table. So, I actually need to. What we cared about now is we're looking for numbers whose products came out 1. That's what we care about. So we found 1 times 1 is equal to 1. We found 7 times 3 is equal to 1. We found 3 times 7 is equal to 1. And we found 9 times 9 is equal to 1. In other words, what is the multiplicative inverse of 1? It's 1. What's the multiplicative inverse of 3?
It's 7.
7. 7 is a unique number, such that if we multiply it by 3, we get 1.
So we can only divide by 1, 7, 3, and 9?
In this system, yes.
That sucks.
Those will be the only ones we can divide by.
Why is that so?
1, 7, 3, 9.
You can just possibly get.
What's that?
I love division.
All right, and notice that when they did have a multiplicative inverse, they only ever had 1. We never have multiple 1 showing up on the same row.
If you love it so much.
No, it's more of 1.
If a 1 shows up, it only ever shows up once. So, now we're going to do a proof of that fact. We're going to prove that if a and zn has a reciprocal, then it only has 1. So we're going to prove that in general, it is impossible to have 2 1s show up on a row, or 2 1s show up in a column.
Okay.
Notice that we can have multiple zeros show up in a column. That was no problem. Multiple 5s showed up in a column. Is it ever possible for multiple 1s to show up in a column?
No.
Or in a row? That's what we're going to prove is impossible. That's what the next proof is. Let A be anything in Zn. We could have picked Z 576. And you still would never have gotten multiple 1s in the same row. That's what we're going to prove.
That is cool.
Pretty crazy what we're about to prove.
We should try it.
You can go ahead and try it. I'll just prove this. We'll see who can handle it first.
Hey Siri.
Build the table for you. You're still going to have to manually check that table for a 1.
True.
No.
It'll take forever.
You say, hey Siri, pull up this table, and then you do the control
Siri.
F1 or
Modular arithmetic table of
Then click ones.
560.
It'll probably pull up a bunch of 1s in numbers that contain a 1, like when 21 comes up. Because we're talking about in Z sub 576.
Right. It'll highlight them, so you can like.
It'll make it faster. Still think we'd be faster off doing this proof. Anyways, let's just prove it. Alright, so if A is something in Zn, then A has at most 1 reciprocal. If it has a reciprocal, it only has 1. It can't ever have more than 1. So we're proving it has at most 1. So let A and Z1 assume by way of contradiction that there exists a B and a C such that B is the multiplicative inverse of A and C is the multiplicative inverse of A. Or in other words, A times B gives you 1 and A times C gives you 1, where B and C are different numbers. We're going to show this is impossible.
Okay.
Alright, how are we going to prove this? I'm going to show you, we assume this, I'm going to show you B is equal to C. We said let B and C be numbers that both make this true, such that they're different from each other. I'm going to prove they're also equal to each other, contradiction. Therefore, B and C can exist. And how are we going to do that? Well, B is equal to B times 1, right?
Yes.
And 1 can be rewritten as A times C.
Right.
So B times 1 is equal to B times 1.
Okay.
With me? Now we're going to use associativity. So B times A times C is the same thing as B times A times C, right? What's B times A?
1.
1. I guess we're using commutativity to go from that to that, but hopefully you can see it. So B times A is 1, so that's the same thing as 1 times C. What's 1 times C?
C.
So B is equal to C, and B is not equal to C. Contradiction. Therefore, A has at most 1 reciprocal.
That was the shortest proof ever.
A lot easier than checking a table. All right. And it proves it for all infinitely many tables you can make. Okay, definition. I've already been kind of using this notation, but just put it out here. If A is invertible, then we use A to the power of -1 as its inverse.
Okay.
And you're going to do a proof. Sorry, the whiteboard died right here. I had to write over here what you're going to prove in your homework problem. That A is equal to the multiplicative inverse of its multiplicative inverse.
Okay.
Okay.
Which you know is to be true in regular arithmetic.
That is true.
What's the multiplicative inverse of 3?
4, 3.
What's the
Negative
multiplicative inverse of
Negative
3?
1 over
7.
3.
-3.
In which world?
In regular arithmetic. Sorry, I thought I said that.
Okay.
In regular arithmetic, what is a multiplicative inverse of 3?
1/3.
1 over 3.
1/3. And what's the multiplicative inverse of 1/3?
3.
3. So the multiplicative inverse of the multiplicative inverse just gets you back where you started.
Yeah.
That's what you're proving in this arithmetic.
That's easy.
And it's going to be pretty similar to what we did right here.
Oh.
I don't know. I'm almost ready to just spell it out for you. We'll let you try and think of it. Pretty quick proof, pretty small, pretty close to how this one's done.
You gotta move your camera.
Thank you. Oh, that would have been awful.
Would have been a real disaster. All those.
This is the first year I haven't had that mistake.
Yeah, I thought you had it earlier this year.
Nope.
That's
Oh, I've drawn off camera a little bit, but no, there's been
There
classes
was
where I
time.
flat out didn't move it.
There
So I
was-
can tell you with the whole lecture and half of it's gone.
But you could hear him.
Yeah, you can hear me.
There was a time towards the beginning of this year that you forgot to start your camera.
Is there?
Like you clicked it, but it didn't click, and then
No,
At
there's
the
one
end of
time
class.
where
I don't think for
it stopped
discrete
recording.
math.
Your camera
In
stopped.
discrete-
Oh, when we were doing a homework review. So it wasn't a lecture, so we're good.
Oh, yeah.
Yeah, I remember that.
Doesn't count.
You're
It
safe.
You're right.
stopped recording.
But we got all the
You
lecture.
get to see.
Alright, we gotta keep turning away. Let's keep turning. Okay, so now we're ready to define division. Let A and B and Z n such that B is invertible, then A divided by B is the same thing as A times B's multiplicative inverse.
Okay.
Right? So go back to Z10. Now what's 2 divided by 7? Well, that's the same thing as 2 times 7's multiplicative inverse. What was 7's multiplicative inverse?
3.
3. 3 is what you multiply 7 by to get 1. So this is the same thing as 2 times 3. What's 2 times 3?
6.
6. So you just figured out that 2 divided by 7 is 6. Right? Obviously. And what's 2 divided by 3? That's the same thing as 2 times 3's multiplicative inverse, which is the same thing as 2 times 7, which is equal to 4. So 2 divided by 3 is 4.
Yeah, that makes perfect sense.
Modular arithmetic.
There's like no pattern to see with it. Unless you like really
you just have
go.
to think about it.
It's usually the answer. This doesn't make sense. Yes, it does. You just have to think about it. Okay,
Dang, I gotta put that on the plaque.
it's true. You just got to think about everything we've done here, and it all makes sense. Because it turns out we slowly build up, making sense, right?
Right.
Okay. What are we proving now? If A and Zn is invertible if and only if and
Relatively.
I have no clue what I wrote.
Relatively?
Relatively.
A and N are.
Relative.
What is relatively?
I have no clue how I did that.
Were you like really sleepy, like late last night or early this morning or something? It was.
He was in the wrong
All right.
group of friends.
So A in Zn is invertible if and only if A and N are relatively prime. Or in other words, their greatest common divisor is 1. So notice going back to this table, all the numbers, if we were looking for a pattern, which of these numbers happen to have a multiplicative inverse?
3, 7, 1, 9.
3, 7, 1, and 9, but what do we notice about those numbers? It's not all the odds, it's not all the primes.
It's all the ones.
What are all the numbers that had a multiplicative inverse? And it turns out it's all the ones that are relatively prime with 10. Or in other words, it's all the numbers such that their greatest common divisor with 10 is just 1.
Interesting.
What's the greatest common divisor of 1 and 10?
That's true.
1.
1. What's the greatest common divisor of 2 and 10?
5. 2.
2. Greatest common divisor of 2 and 10 is 2. What's the biggest number that goes into both 2 and 10?
2.
2. What's the greatest common divisor of 3 and 10?
Oh, divisor. I was thinking factor.
3 remainder 1.
Greatest common factor.
Same thing, yeah.
Okay, greatest common factor. Is that how we write it here?
Yeah.
No, we call it GCD. We call it greatest common divisor. Greatest common factor, greatest common divisor, same thing. Alright. What's the GCD of 4 and 10?
1. Oh,
2.
2.
2. They're both even. What's the GCD of 5 and 10?
2.
5.
5.
Oh,
2 does not go into 5.
Not in the slightest.
I was even thinking that.
What's the biggest number that goes into 5 and 10? 5. What's the biggest number that goes into 6 and 10?
2.
2. What's the biggest number that goes into 7 and 10?
1.
1.
What's the biggest number that goes into 8 and 10?
4, 2.
2. What's the biggest number that goes into 9 and 10?
0, 1.
1. So, all the ones where the answer was 1 were the ones that had a multiplicative inverse. We're going to prove that that's always the case. Lost where we were. We were right here. Alright, prove.
Invertible.
A and Zn is invertible. It has a multiplicative inverse. It has a reciprocal.
Okay.
If and only if A and N are relatively prime,
Okay.
or their GCD is equal to 1. Alright, let's go this way first. Assume A and Zn is invertible. What does that mean? It means that there must exist some element that's its multiplicative inverse.
Yeah.
So there must exist some A inverse such that A times A inverse is equal to 1. Right?
That's right.
Yeah.
Right? Which is the same thing as using the definition of multiplication here. A times A inverse mod N is equal to 1. Right?
Yeah.
Okay. Now, what I said as our note here, we're going to use again. a number mod n is identical to a number plus some integer multiple of n. So a times a inverse plus some integer multiple of n is going to be equal to 1 for some integer k. We don't know what it is. But there is some k that makes that true. Right? Okay. So then, using what I told you was the second most important theorem in number theory, we just barely got, I'll change the order a little bit. So this to here is just changing the order.
Okay.
Some integer times a plus some integer times n can always be written as their GCD. If it comes out 1, that has to be their GCD. So, since I can write some number times a plus some number times n equal to 1, where those are integers, I know that the GCD of a and n is equal to 1. That's what it means to be relatively prime. So you prove two numbers are relatively prime. You show that you can find two integers such that two integers times those two numbers, when you add it all together, comes out 1. So we're done with that direction. I barely showed that if a is invertible, then the GCD of a and n is equal to 1. Follow that? No? I don't know Morse code. Alright, next one. We're going to prove the other direction. So let a and zn such that the GCD of a and n is equal to 1. Well, what does that mean? That means that there must exist two integers x and y such that ax plus yn is equal to 1. Using that second theorem, I told you was the second most important theorem we're going to use over and over again. So then, what do? I'm going to solve for ax, or in other words, just put the yn to the other side. So ax is equal to 1 minus yn. Now what am I going to do? I'm going to mod n both sides. If these two numbers are equal, when I mod it by n, I should still get the exact same thing. Right?
Right.
So I'm just going to mod both sides by n, from here to here. So we're going to mod that by n, we're going to mod that by n. Okay. Now, what is y times n mod n?
1.
What is y times n mod n?
0.
Why?
0!
Oh.
Right?
Why?
Oh,
Yeah,
I really tried spelling this one out for you. Wait a second. No, I didn't. That's good. So, y mod n, or y times n mod n is 0. 1 minus 0 is
0 or 1.
1. And 1 mod n is always
1.
1. Okay. So then we get
1. N equals 1.
a times x mod n is equal to 1. So this whole side simplified to 1. So now we're like this. You with me? Now I'm going to mod the x by n, and then mod the whole product by n. So I'm going to take this, and I'm just going to mod that x by n. Doesn't change anything.
Okay.
Look, here's what I'm thinking so far. A times x is mod n is equal to 1. So this x is going to be the multiplicative inverse of a. I got a times something is equal to 1. Right?
Yes. Yeah.
Imagine we're in Z10 here. So we're over here. And I just barely found out that 3 times something is equal to 1. I know 3 times x is equal to 1. The one problem I have is I don't know if that x is in Z10. Maybe I found out that 3 times 97 is equal to 1.
In Z10.
In Z10. So maybe so far I know that 3 times 97, when I mod it by 10, is equal to 1.
Okay.
That gives me that z times 7 is going to be equal to 1. If I mod that number by 10 first, it won't change anything. And then it will give me my actual multiplicative inverse. So this x right here, thus far, could be some number like 97, rather than the 7 we're looking for. You see what I'm saying?
Yeah.
So I'm saying, let's do that. Let's take a times 97 mod 10. Let's take that 97 and mod it first, so we can get to the actual 7. You with me? Okay. But what is x mod n? I can rewrite 97 mod 10 as 7 plus some integer multiple. I can rewrite 97 as 7 plus some integer multiple of 10. Or in other words, 9 times 10. So rather than having the full 97 there, I'm going to split that into the 7 plus 90 and mod that by 10.
Okay.
You with me? Okay. Now, when I mod that by n, what am I left with on the kn?
Just the x.
Right, that part goes out, the kn goes out, that's going to be the 0. All we're left with is now the x prime. So if x were initially 97, our x prime is going to be just our 7. So then a times the x prime mod n is going to be equal to 1. A times x prime mod n is going to equal to 1, which gives me that a times x prime is going to be equal to 1. So I just needed to take x, which was 97, and convert it to something in Z10. Find its corresponding element in Z10. Or in other words, mod it by n first. And modding it by n is the same thing as adding some integer multiple of n. Make sense? So we replaced x mod n here with x prime plus kn. This mod n is this mod n. Oops. That's probably confusing you guys. Ah. I have it written that here twice. Sorry. X mod n is the same thing as x prime plus what I use for my integer.
K.
K times n. Sorry, that's probably confusing.
Oh,
There
yeah,
we go.
now that-
Okay, sorry.
Yeah, okay.
I had two mods in there.
I was gonna ask that.
Okay, x mod n is the same thing as x prime plus some integer multiple of n. Okay. Where this x prime now is going to be our remainder. X prime is our remainder when we take x and divide it by n.
I'm wondering, you have a times x mod n, and then you're giving the x mod n, but then you're leaving the mod n to also multiply the answer of that again.
The mod n out here is for the definition of when we go, that mod n stays there, and then that's for switching back to our definition.
But shouldn't that mod n only apply to the a now, because you already applied it to the x?
We can mod this by n again if we want. That's probably why I put that in there. So 1 was canceling out. Probably a bad idea. Here, let's just clean up. Let's just make this super clear. All right, x mod n in and of itself is going to be x prime being the remainder plus k times n, right?
Yes.
And then we have mod n, where 0 less than or equal to x prime is less than n. With me?
So you can mod something as many times as you want.
You can mod it as many times as you want, it doesn't change anything.
That makes sense.
Modding it is kind of like just putting parentheses around it. So then you can mod it again to get rid of that, leaving you with this, and then we leave out last mod n just to convert back to our definition. But yes, you can mod your answer by n as many times as you want, anytime you want, to help simplify the number as you're working with it. Because it turns out 97 and 7 are basically the same mod 10. So if we look at the mod 10 equivalence classes, both 97 and 7 will be in there. They're somehow equivalent. Which they are. Going back to older thinking, 97 is equivalent to 7 mod 10. Anyways, so there we go. There we have it. A and Zn is invertible if and only if its GCD with n is 1. Alright, so now how do we use this result? Because it turns out this is very useful. So now let's look in Z431, and we're going to want to do division in this system.
Okay.
So we can't create some big multiplication table.
Okay.
But we got to figure out how to find a multiplicative inverse. So in Z sub 431, I wanted to calculate 1 divided by 29. You with me?
It's 9.
It's definitely not 9. We're in Z sub 431.
It comes out as 1.
No. So
Oh, okay.
1 divided by 29 is going to be the same as 1 times 29's multiplicative inverse. right? So we need to find 29's multiplicative inverse. Or in other words, we need to find the x such that x times 29 gives us 1. That would be 29's multiplicative inverse.
Yep.
So that's what we're trying to solve. Now, it turns out Euclid's is very useful for this. So I told you we're going to use Euclid's algorithm all the time. And you got to hang in there. And then it's just going to keep coming up. So here's where it just starts coming up and keeps coming up. In problems like this. So going back, we need to find the GCD now of 431 and 29. I'm looking for 29's multiplicative inverse in z sub 431. That's where my 431 and my 29 come from. So 431 is our n, 29 is the number I'm looking for the multiplicative inverse of. I'm looking for the multiplicative inverse of 29. So I want to use Euclid's for 431 and 29. Now I already know that the greatest common divisor is 1. 29 is a prime number, 431 is probably also a prime number. More importantly, 29 is prime, 29 doesn't go into 431. So I already know that their GCD is 1. So I don't care about figuring out what their GCD is. It's just going through the steps of Euclid's algorithm is what's going to be really useful. That's why I said it's important for you to memorize Euclid's algorithm. It's not so you can figure out how to calculate greatest common divisor. Any computer can do that just like that. It's like you can do this process that we're about to do. Alright, so 431 is equal to 14 29s plus 25. Right? Do math in your head real quick. Okay, yeah.
Yeah, okay.
Alright.
You can take my word for it on that one. From here on out, you should be able to check it. Now we got to do 29 divided by 5. 29 is equal to 125 with the remainder 4. Now we need to do 25 divided by 4. 25 is equal to 6 4s. Did I say 24? We need to do 25 divided by 4. 25 is equal to 6 4s plus 1. That's not us. So I get that the GCD is 1. Surprise, surprise. Remember extended Euclid's though. We also solve for the remainder in each problem. So I take this, solve for the 25. 25 is equal to 431 minus 14 29s. 4 is equal to 29 minus 125. 1 is equal to 25 minus 6 4s. You with me? Now I'm looking for a product of 29 and some number such that it's equal to 1. This is going to be the 1 that it ultimately equals. So take this one, that's where the 1 comes from. 1 is equal to 25 minus 6 4s. What am I going to do? I'm going to do a substitution for 4s, simplify, then a substitution for 25s and simplify. And that is going to give me 1 is equal to a product of 29s and 431s. That's big picture where we're going. So 1 is equal to 25 minus 6 4s. Sub out my 4s using this substitution. 1 is equal to 25 minus 6 4s.
Okay.
Now collect all my 29s and 25s. So 1 is equal to 7 25s minus 6 29s. Now I'm going to sub out all my 25s using this. So down here I have 7 times 25 minus 6 29s. Now collect all my 431s and my 29s. So I get 1 is equal to 7 431s minus 104 29s. You with me?
Okay.
Now notice, if we now mod by 431, what is this equal to?
0.
0. And so I got a number times 29 mod 431 is equal to 1, which is what we're after. A number times 29 gave us 1, because this 431 is going to go to 0. So that was the whole trick. I was trying to write 1 is equal to a product of some number and 0, which won't matter, and then some number and 29. 1 is equal to the sum of some number and 0 plus some number and 29. That some number and 29, that some number is going to be the multiplicative inverse.
Okay.
That's the whole trick. So, mod both sides by 431, and what do we get? This goes to 0. What's 1 mod 431?
1.
Just 1. And so we get this product, mod 431 is equal to 1. Now our only problem is that negative 104 is not in our set Z sub 431. How do we get the corresponding number in Z sub 431?
Mod it.
Mod it by 431.
Yeah, we mod it by 431, which is the same thing as doing what? Just adding 431. Remember, if you add 431, you don't change your number. It's like when you're looking at a clock. If you go ahead 12 hours, you didn't change anything. If we go ahead 431 places, that's cycling through the entire set, getting us back where we started.
Yeah.
So, what's negative 104 plus 431?
329.
430.
327, right?
Oh, yeah. Why?
No.
What's 431 minus 104?
Three.
327.
Oh, okay, I thought we were stuck for some reason. Okay, everyone's good. Alright, so 431 minus 104 is 327. So 327 times 29 mod 431 is going to be 1. And you can check it on your calculator if you want. We found the number. And that's the only number. Now imagine if we tried to do this by hand. What a pain that would be.
Quite.
I know Euclid's algorithm felt like a bit of work, but it saved us from having to check. If we just start checking 1, 2, 3, 4, we would have had to check 327 numbers.
Okay.
So, much faster.
Yeah.
You suspicious of something?
No.
So, 327 times 29 is equal to 1. Or in other words, 327 is 29's multiplicative inverse. So now we can solve our problem. What's 1 divided by 29? That's the same thing as 1 times 29's multiplicative inverse. So it's 327. So 1 divided by 9 is 327.
Logic.
Or 1 divided by 29 is 327. Yeah.
I have a question on the table again.
Okay?
If you were to add the 10th row of Z sub 11, so if you make that Z sub 11,
It changes all the numbers.
wow. How? Wow.
Because now we have to mod by 11. 2 times 5 in Z11 is 1.
Oh, yes.
Or sorry, is 10. 2 times 5, this would have been 10.
Yeah, that makes sense.
3 times 5 now would have been 4. So it's drastically different. Same patterns do not hold anymore. Good. Okay, anyways, so there we go. That's how we can find a multiplicative inverse. You're going to have to find one of these on your test.
Okay.
I'm going to give you something like find the multiplicative inverse of 29 in Z sub 431. And you're going to have to go through the steps. It's going to be a pain. And just checking all day on your calculator if it works is not a good way to try and find that number. You'll take the whole test doing that.
Yeah,
You need to know this process.
You can check this, right? Can you?
Yes, you can check this. So, how would you check this? You do 327. Hopefully my batteries aren't dead. Okay, we got 327 times 29 is equal to 9,483. So I do 9,483 divided by 327. Oh, not divided by 327. Oops. Divided by, I want to know its remainder when we mod by, what were we modding by?
431.
431. So divide by 431 and figure out the remainder. So 9483 divided by 431 is equal to 22.00023. Take that, subtract away the 22. So now I'm left with just a 0.00023. Take that and multiply it by the 431. And it comes out 1.
That was weird.
I figured out what the remainder was, the decimal part.
So is that 1 over 1431?
Yes. You could also just check that. You could have looked at the decimal and then checked, is that the same thing as 1 divided by 431?
Yeah.
Yep. So yeah, we were right. But you see, it's a few steps on the calculator just to check one of these numbers. Checking all the numbers up to 327 would have taken a bit. So much better to use Euclid's. Okay. So now let's see if we can solve this problem. In Z, 431, what's 30 divided by 29? So now we're looking for 30 divided by 29. What is it?
Euclid's.
Well, we don't have to use Euclid's again, because this is the same thing as 30 times what?
Oh, wait, it's 327.
327. So now we just need to figure out what that is.
Oh, yeah.
30 times 327 is equal to 9,810. So this is equal to 9,810. Oops.
300.
Did I say it wrong?
9,800.
Okay.
And 10 mod
431.
431. Now you can keep subtracting 431s from that until you get a remainder if you want. Or you can calculate the remainder however you want. Or you can just do the division, take the bull by the horns. I guess we won't use a calculator. Now just divide it and see what our remainder is. So we're taking 9810 and we're dividing this by 431. Starting here, how many times does 431 go into 981? Twice. 2 times, which is going to give me 862. We're going to do the subtraction. What are we going to get? We got 1 here, but what's 81 subtract 62? Come on, come on. 19. 19, bring down the 0. Now, how many times does 431 go into that?
3.
2.
No, 3 would get us to 1200, so it can only be 2. 2, which once again
862.
is going to be 862.
What?
And we're going to subtract. Did I mess something up?
No, you're good.
All right. So the 11 subtract the 8 is going to be the 3. The 90 subtract the 62 is going to be the
18.
18. No, 28.
28. So with a remainder of 328. So there we go. 9810 mod 431 is 328.
Yep.
Just gives us a remainder. Okay, so we were able to figure out that problem now. All right, let's do something a little bit different. Let's solve congruences now. Shifting gears a little bit. Now we're going to be doing congruences. Let's solve congruences for solutions. This is kind of like finding solutions to linear equations that you're used to in algebra. So let's start with this one. I want to know all the x's that are congruent to 4 mod 10. The way I'm going to write mod 10 is just a side parentheses like that. So we're looking for x is congruent to 4 mod 11, or in other words, what are all the numbers that are congruent to 4 mod 11? What are all the numbers such that when you divide it by 11, you get a remainder of 4? What's the first number? Give me a simple number that I can divide by 11 and have a remainder of 4.
15.
Well, that was a little harder than what I was after. 15's one. There's an even easier one.
Oh,
4! 4 divided by 11 is
4.
0 with a remainder of 4. All right, it's going to be 4. It's going to be 15. What else is it going to be?
26.
26. What else is it going to be?
37.
37. He sees it. What else is it going to be? Not Jeremy. Ah, Debbie sees it. Not Debbie or Jeremy. What's next?
59.
59. And obviously, we're just adding 11s now.
Naturally.
Because if the remainder is 4 for this, every time we add an 11, when we divide by 11, that's just going to be 1 more to the quotient. So these are all the numbers such that when you divide by 11, you're going to have a remainder of 4. What's 59 divided by 11? 5, which gives us 55, with a remainder of 4. This is 4 with a remainder of 4, 3 with a remainder of 4, 2 with a remainder of 4, 1 with a remainder of 4, 0 with a remainder of 4. We could have also put on, going the other way, what would the next number here be?
What? You can't go.
What's another number equivalent to 4? Sure we can.
Remainder 7. Or
Negative 7. Negative 7, when you divide by 11, has a remainder of 4. You can't divide by 11, so we can't mod by a negative number. But the number we're dividing can be negative. So we can do negative 11, negative 18, da 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 da. Or in general, if we want to write this out in general, x is anything of the form
K11.
4 plus k times 11. Pick any integer for k, and that's your answer.
Okay.
Make sense? So x equal to that for all k and z. If we want to be super explicit. There's all the solutions to that equation. Okay, let's try a slightly more complicated one. I tell you, I want all the numbers x such that 5x is equivalent to 6 mod 8.
What do we do with that 5?
Yeah, that's a little bit hard to think about. What can we do with that 5? Let's go back to regular algebra. If I would have told you that 5 times x is equal to 6, what would you do?
Divide the 5 to the other side.
Divide 5 to the other side. What's another way that we say divide 5?
Multiply by 1/5.
Multiply by 5's multiplicative inverse. If this is true, then 5's multiplicative inverse multiplied to both sides is still going to be true.
So what's 5 multiplied to?
And so we get x is equal to 6 times 5's multiplicative inverse. We got to do the same thing over here. What is 5's multiplicative inverse in 8? Now you could use extended Euclids in this one, but this is a small enough number, just 8, that you could probably just think about it.
3.
5 times what gives you 1? What's 5 times 3? 15. Mod 8 is 7.
1/5.
No, it's gonna be
5 times 1/5 equals 1.
We're now over here. So now we're modding by 8.
Is this one?
If we're modding by 8, what's 5's multiplicative inverse?
60.
5 times what gives us 1 when we mod it by 8? An integer. Give me a hint. It has to be a number between 0 and 7. It's 5. What's 5 times 5?
25.
25. What's 25 divided by 8? 4 with a remainder of 1.
Right.
So it's 5. So we're going to multiply both sides by 5. So if I know this is true, then 5 times x is congruent to 6 times 5 mod 8.
4 with the remainder of 8.
It's 5, or 3 with the remainder of 1.
3 with the remainder of 1.
I don't know what you guys are talking about.
This is not first.
You just said something weird.
Oh, I did?
You said 4 remainder 1, not 3 remainder 1.
8 goes into 25 3 times.
You said
4
4 times.
Yeah, you said 4.
Okay, sorry. 3 times with the remainder of 1. Alright, you're with me. So 5 times 5 is 25, mod 8 is 1. So this is the same thing as 1 times x is equal to 6 times 5 is,
30.
mod 8 is,
30 mod 8 is 3 remainder 6.
remainder of 6.
It's 3. Yeah. 6.
Just count by 8. 8, 16, 24. And then you need 6 more to get to 30.
I got 28 3 times.
So 6. Or in other words, x is congruent to 6 mod 8. Or in other words, now, what are all the solutions? That's going to be x equal to 6 plus any integer multiple of 8. Will work.
We just got rid of the 5.
Yeah, the only trick there was canceling out the 5.
We just got rid of it completely. Had the same answer.
Well, it just so happened that 6 times 5 was 6, but that's not always going to be the case. So that was just a coincidence. So here's all the x's that make it true. So if I plug 6 into here, it should work. Let's try that. What's 5 times 6? What's 5 times 6? 30. 30 mod 8 is
6.
6. 6 is congruent to 6 mod 8. Okay. Let's try another one. Let's plug in 1 for k. So 6 plus 8 is
14.
14. So let's plug in 14 for x. 5 times 14 is?
2.
5 times 14 is 70.
Oh, yeah.
70.
I'm so
What's 70 mod 8?
2.
It is 8.
It's 2.
Remainder 6.
It's going to be 6.
Is
8 times 8 is 64. Plus 6 gets us to 70.
9 times 8 is 72.
I don't know where you're getting 9. Oh, 9 times 8 is 72.
So it's
So
2.
9 times 8 is 72.
We got 70.
We have 70. So you overshot it. You need to go back one. So you can't use 9 times 8, you need to use 8 times 8 is 64, plus 6 more gets us to 70.
This is true.
So yes, when you pick one for k, it also works. And you can pick anything you want for k, and it will always work. Okay, surprise, surprise. Now let's do one slightly harder. Let's solve a system now of linear equivalences. So now I know that x is congruent to 1 mod 7, and I know that x is congruent to 4 mod 11. I want you to find all the numbers x such that when you divide by 7 you get a remainder of 1, and when you divide by 11 you get a remainder of 4. You with me?
Yeah.
Alright, let's just focus on all the x's that make this one true. If I know that x is congruent to 1 mod 7, what are all the x's that make that true?
2 times 7 is
X equals to 1 plus some integer multiple of 7.
2, 4.
1, 8, 15. Let's give you all the ones that make this one true.
What?
What's 1 mod 7?
1.
1.
Yes.
Okay. What's 8 mod 7?
1.
1. What's 15 mod 7?
1.
22 mod 7?
1.
29 mod 7?
1.
30 mod 7? 2.
2.
Just making sure Debbie wasn't just saying 1 every time. Losing you?
No.
Yeah.
Yes.
Okay.
Okay.
We're looking for all the numbers that are congruent to 1 mod 7. We're looking for all the numbers such that when you divide by 7, you get a remainder of 1. I'm saying it's these numbers, where k is any integer. Alright, let's write this out. What is 1 divided by 7?
1.
0 with a remainder of 1. Right? What is 8 divided by 7?
1.
1 with a remainder of 1. What is, let's pick some number for k.
3.
Let's do 9 for k. What's 9 times 7?
56.
63.
63.
Right.
9 times 7 is 63, plus 1 is
64.
64. So let's look at 64 divided by 7. How many times does 7 go into 64?
9.
7 times.
9 times, which is going to be
64.
63.
Or 63.
Minus, we get 1, so it has a remainder of 1. Because we multiplied by 9 to find our 64.
Oh, that's really.
That is the case.
In general, if we replace 64 with k times 7 plus 1, and we divide by 7, our answer is going to be k
Remainder 1.
with a remainder of 1. How many times does 7 go into k times 7 plus 1? K with a remainder of 1.
Every answer is true.
These are all the numbers that make this equation true.
Oh, that's how you put it.
That's all I've done so far.
That's really easy.
Well, we got to find the ones that also make this one true. Only some of these are also going to make this one true.
Okay.
So this is for all k and z. All right. So those are all the ones that make this one true. But we also need them to make this one true as well. So I also need to find all the x's such that x is congruent to 4 mod 11.
So 4
But I know that x has to be the form 1 plus k times 7, so make that substitution. So I want to find all the k's such that 1 plus 7k is congruent to 4 mod 11.
Can't 4 mod 11 turn into 4 plus k 11.
Yeah, we can work with this. So now we just need to solve this. First thing we're going to do is what? Subtract 1 from both sides. Same thing you know and love.
Yep.
So then we got 7k is congruent to 3 mod 11. Now I want to multiply both sides by 7's multiplicative inverse. What is 7's multiplicative inverse mod 11?
3.
4.
4.
4? Yeah, it's going to be something. Count by 7's until we are 1 more than the multiple of 11.
Okay.
7, 14, 21, 28, 35, 42, 49, 56. There it is,
Oh.
56. That took 8 counts. So 8 is its multiplicative inverse. In other words, what's 8 times 7? That's 56. What's 56 divided by 11? 5 with the remainder of 1. So 8 is 7's multiplicative inverse. right? When we mod by 11. So then 8 times 7 times k is equal to 3 times 8, all mod 11. 8 times 7, we already know that's 56, mod 11 is 1, so that's just k. Oops, these are congruences. Is congruent to 3 times 8 is,
24.
mod 11 is
3.
4.
2.
2.
Oh, whoops, yeah.
3 times 8 is 24. How many times does 11 go into 24? 2 times with the remainder of 2. So that's congruent to 2 mod 11. What are all the solutions to this? That's going to be k equal to 2 plus m times 11. Right?
Right.
So k has to have this form, where x has to have this form. So now finally go back and get our x. We know x was equal to 1 plus 7k, but k is equal to 2 plus 11m. And when it's all said and done, that's equal to 7 times 2 is,
14,
plus 1 is
15,
15, plus 7 times 11 is
77.
77m. This is going to be true for all m in z. Pick any integer m and this will be true. For example, let's pick m to be 0. 15 better satisfy both these. What's 15 divided by 7?
1.
2 with the remainder of 1. What's 15 divided by 11? 1 with the remainder of 4. So 15 makes both of these true.
Yeah.
And now, since 77 is a multiple of 11, and since 77 is a multiple of 7, if you add 77 to your answer, you're not going to change anything. Because 77 mod 7 is always 0, and 77 mod 11 is always 0. So now you're adding as many zeros as you want. So 15 plus any number of zeros will satisfy both those.
Okay.
Make sense? Okay, so that's how you're going to solve the system of linear equations. All right, now let's move on to factoring.
Is the test next week?
Sure hope so.
Is it?
Sure hope so.
I don't.
If I can get through all this material, it will be.
Spring break.
Yeah.
Oh, it is? Thank you for telling me that.
You're welcome.
Just a surprise.
I mean, it wouldn't be the first time we shot it on a day.
I don't know if I've ever actually showed up on that.
We showed up and took our final.
On your day
Yeah.
off.
Oh, you guys did. Yeah, I did.
Oh, yeah.
I didn't even know you guys were going to show up.
We don't have lives.
It's a good way to spend life. All right. The next section is just on factoring.
Yeah, but on the day.
Factoring numbers. And, huh?
There's snow outside. It's the same.
You're gonna-
And we're going to be working our way up to the fundamental theorem of arithmetic. Try and get you to the point where you know the fundamental theorem of arithmetic. What is a fundamental theorem of arithmetic? It says basically every positive integer has a unique prime factorization. And hopefully since grade school you've been finding the prime factorizations of numbers.
We have.
So we're going to prove the thing that says you can do that. So what's the big theorem we're going to be proving? If n's a positive integer, then n factors into a unique product of primes, ignoring order, or in other words, it has a unique prime factorization. In other words, if I gave you 30 and it says, what are the prime factors of 30?
5, 3, 2.
They're 5, 3, and 2. But they're also 2, 5, and 3. They're also 3, 2, and 5.
5, 3, 2.
Are these any different?
No.
What about 5?
No, they're only different in order. That's what this theorem is saying. It's saying if n is a positive number, then it has a unique product of primes. It factors into a unique product of primes, ignoring order. Or in other words, it has a unique prime factorization. That's the way I'm going to say it. So here's the unique prime factorization for 30. 5, 3, and 2. Those are the only primes you could take and multiply together to get 30. There aren't any different ones. You had to use those exact ones. Or 12, 2, 2, and 3. We don't care about what order you write them in.
Okay.
That's its unique prime factorization. Let's try a different number. Let's try 60. What's 60's unique prime factorization?
5, 3, 2, 2.
5, 3, 2, 2. You did that kind of fast. Let's go over how you would normally do this. You did it with a little tree. You start with 60. What times what gives you 60?
6 times 10.
5 and 12.
6 times 10, 5 and 12. Doesn't matter which of those we use. Just use one of her first. 6 times 10. What times what gives us 6?
3, 2.
2 and 3. We have primes now, so we can't factor those anymore. What gives us 10?
2 and 5.
2 and 5. We can't, those are prime, we can't factor them anymore. So the unique prime factorization was 2, 3, 2, 5, which is what we have there. Make sense? All we're doing is proving that we can do this. That's the big goal of this chapter.
Joy.
Oh, joy. All right,
Joy.
note. What about the number 1? What are the prime factors of number 1?
1 and 1.
Those aren't prime numbers. 1 is not a prime number.
What? No, it isn't.
Yeah, so what is the unique prime factorization of 1?
Itself.
It's the empty product.
64.
Wait, 1 is 2 prime. Why is 1 not prime?
Take the product of all the primes.
That's pi.
Yeah, pi is our product symbol.
Oh, yeah.
For all the prime I don't know. For P's prime factors, I'm not sure the way to write this so that you'll understand it. Going back to here, do you remember what 0 factorial is equal to?
Yeah.
1. The empty product is 1. What is the unique prime factorization of 1? The empty product.
It's only multiplied.
Take
by
the
1.
empty product of prime factorizations,
You can't. Oh.
and you get 1. So 1 is the one weird case that might throw you for a loop. Is 1 an exception to the rule? No. 1 has a unique prime factorization. Take the empty prime factorization. That gives you 1. Take just 2, that gives you 2. Take just 3, that gives you 3. Take 2 and 2, that gives you 4. Okay. So 1 is not acceptable. Alright, we're going to do some side proofs working our way up to this proof. So our first side proof. Let a, b, and p be integers where p is prime. If p divides the product of a and b, then p divides a or p divides b.
True.
If p is a factor of their product, p has to be a factor of either the first term or the second term. Right?
This is the case.
This is the case. If I know that 2 divides 60, and I know that 60 factors into
5,
15 and 4, I know that 2 has to divide 15 or 2 has to divide 4. That's what we're saying.
Okay, yeah.
So if a prime divides a product, it has to divide either the first term in the product or the second term in the product. That's what we're going to prove. So let a, b, and p be integers such that p is prime, and p divides the product of a and b. Assume by way of contradiction that p does not divide a or b. What does it mean to not divide a or b? It means p does not divide a and p does not divide b. Don't forget our logic here. If it's not alpha or beta, that's the same thing as not alpha and not beta, right? If p does not divide a or p does not divide b, that's the same thing as saying p does not divide a and p does not divide b. So, assume by way of contradiction that this is false, which is what this says, that p does not divide a and p does not divide b. Just make sure I'm not losing you in basic logic there. Good with the basic logic? Okay. Since p does not divide a, then the GCD of a and p has to be 1. How do I know that?
Because that's how it works.
Yeah.
Because p is prime. P is a prime number. What are the only divisors of p?
1. And
1 in itself. Now, if p doesn't go into a, then that means p isn't a factor of a. So the only factors of p are 1 in itself. If p is not a factor of a,
Then it's 1.
then the greatest common factor that both a and p have is just 1. Your prime factors are just 1 and p. You for sure don't have p as a factor. Therefore, your greatest common factor is going to be just 1. So since p doesn't divide a, the GCD of a and p is equal to 1. And since p doesn't divide b, then the GCD of p and b is equal to 1. Now, using that very important algorithm, or that very important theorem I told you from last week, what does it mean for two numbers, GCD to be 1? It means that there exist two integers x and y such that ax plus py is equal to 1. And since the GCD of b and p is equal to 1, that means there exist two integers, z and w, such that b times z plus p times w is equal to 1. With me so far? There exists x and y such that ax plus py equals 1, and there exists z and w such that bz plus pw equals 1. Alright? So now I'm just going to calculate 1 times 1. I'm just going to get hairy. So make sure you can follow this. What's 1 times 1?
1.
1 times 1 is equal to 1 times 1. With me?
Mm-hmm.
Which now, do the distribution. Put those two together, that gives us this, right?
Yes.
Put those two together, that gives us this.
Yep.
Put those two together, that gives us this.
Yep.
Put those two together, that gives us this.
He's good.
Alright, now notice, for each of these terms, p goes into them. I can factor p out of this, right?
Mhm.
I can factor p out of this, right? I can factor p out of this, right? I can factor p out of this, right?
No.
Yes. How do I know I can? Because we assume all the way at the top, p divides a times b. So I know p goes into a times b. So p goes into this, p goes into this, p goes into this, p goes into this. So p goes into this whole thing. Right?
Okay.
So p times something is going to equal 1. Or in other words, p divides 1. I have a prime number dividing 1.
Right.
What are the prime factors of 1?
1 in itself. Or
It doesn't have any.
no.
1 has the empty prime factorization.
It still makes no sense to me.
I cannot get a prime number divides 1. That statement is always false.
What? Why?
Yeah.
Does 2 divide 1?
Yeah.
2 goes into 1 evenly. Is 1 a multiple of 2?
Oh, divide.
No.
I'm getting that confused.
I'm not writing 1 divides p. Okay, that's always true for
Well,
any
1 and 2
integer I put
kind of
there.
break the law.
integers now.
I'm saying p divides 1. Is there any integer? Is p ever a factor of 1 in other words?
Yes. When 1 is.
What p is 1?
P we know is prime. What's the smallest prime number?
Not 1.
2. So does 2 work? Does 2 divide 1? No. What about 3? No. What about 5? What about 7? What about 11? What about 13?
How is 1 not? Never mind.
By definition.
Figured this out.
Going all the way back to prime and composite, we define these things.
Okay.
Okay, so p divides 1, a prime divides 1, that's always impossible. So there's our contradiction. Therefore, p divides a or p divides b. Has to divide one of the two. If it divides a product, it has to divide one of the two. Maybe both, but at least one of the two. Make sense? Okay, that was our first proof. Second proof. A little bit more hairy, but not too bad. If P, Q1, Q2, Q3, Q4, Q5, Qn are all prime, and P divides the product of all those prime numbers, then P had to be equal to one of those prime numbers. So if P divides Q1 times Q2 times Q3 times Q4, all the way up to Qn, where all those Q's are prime, and P's prime, then there had to be some I between 1 and n, or in other words, there had to be one of these terms such that P was equal to one of those terms. Could have been equal to multiple of those terms, but had to be equal to one of those terms.
Yeah. Okay.
That makes sense? What we're trying to prove? If I know that 3 divides 39, which is equal to a product of, represent this as a bunch of primes, that's 3 times 13. So when I represent that number as its products of primes, if I know 3 divides it, 3 had to be one of those factors. If I have a product of a bunch of primes here, and P divides the product of a bunch of primes, P had to be equal to one of those primes.
Okay.
That's what we're saying. All right, we're going to prove this by induction. Base case. Observe that if P just divides one prime number, then P has to be equal to that prime number.
True.
True. If P's a factor of another prime, they had to be equal to each other. Because what are the only factors of Q1? 1 in itself. Can P be 1? Nope. So its only other factor is itself. So if a prime divides another prime, they have to be the same thing. Because the only factors of a prime are 1 in itself, by definition of a prime. Okay, so that's our base case. Now we assume that the statement is true when n equals to k. So assume that anytime you have k primes listed together, a product of k primes, p has to be equal to one of those k primes. If p divides a product of k primes, p has to be equal to one of those k primes. We assume that. Remember the logic for proof by induction. We prove that the statement is true for 1, or in other words, that 1 is in A, where A is the set of all things that make it true. And then we show that if k makes a statement true, that implies k plus 1 makes a statement true. That's our logic for induction. So we proved 1 makes a statement true. We're going to show that if k makes a statement true, k plus 1 also makes a statement true. Therefore, every number makes a statement true.
Okay.
So assume that k makes a statement true. Now I'm going to show that makes k plus 1 makes a statement true. Then if p divides the product of k primes times 1 more, so now the product of k plus 1 primes, I know that p must either divide all those primes, or p must divide this last prime. How do I know that? My proof over here. If p divides a product of two numbers, p either divides the first product, or p divides the second. Right?
Yeah.
That's just using exactly what we proved over here.
Mm-hmm.
If p divides this times this, it has to either divide this, or it has to divide this. That was the previous proof. Now, if p divides this, then I know that p has to be equal to one of those primes by assumption. That's what we assumed up here. We assumed that the statement is true for k. This is the statement for k. If p divides a product of k, then I know that p has to be equal to one of those primes between 1 and k. That's by assumption. And now if p divides k plus 1, p has to be equal to k plus 1. If p divides a single prime, p has to be equal to that single prime.
P equals K.
So either the q that p is equal to is between 1 and k, or the p that q is equal to is the k plus 1. In either way, either case, p is equal to q sub I, where I is between 1 and k plus 1. So it's going to be one of those. So I just by showing that the statement is true when you're multiplying k primes together. It's true when you're multiplying k plus 1 primes together. Therefore, in general, if p divides the product of n primes, p has to be equal to at least one of those primes, q sub I, where q sub I is between 1 and n. Or in other words, has to be one of those primes. Make sense there?
Yeah.
Pretty simple proof by induction. Alright, now the masterpiece.
Can we just skip it?
No! Skip the fundamental theorem of arithmetic.
Yeah.
How do you skip the fundamental theorem of arithmetic?
I thought that was just the first one we did.
No, now we're doing the fundamental theorem of arithmetic. We're proving every positive integer has a unique prime factorization. Gotta know your arithmetic. Alright, let's do it. Okay, if n is a positive integer, then it has a unique prime factorization. Or in other words, then n factors into a unique product of primes ignoring order. I may call it the unique prime factorization because that's what everyone calls it. Alright.
Logic checks out.
We're going to do this with the smallest counterexample method. So I'm going to let x here be the set of all positive integers that don't have a prime factorization. And I'm going to show that x is empty.
Yes.
So I'm going to show that would show that every number has a prime factorization. X is the set of all the integers that don't have a prime factorization. I'm going to show x is empty. Therefore, every integer has a prime factorization. And then after that, I'm going to show and its prime factorization is unique. So first I'm going to show there is a prime factorization. Then I'll come back around and show and that prime factorization is unique. You with me? So first I'm just going to show that you can factor any positive integer into a product of primes. So I'll let big X here be all the ones that you can't factor into a product of primes. I'm going to show it's empty. We'll do it by way of contradiction. But first off, we know that 1 has a prime factorization, namely it's the empty product. So it can't be an X. And we know that any prime P also can't be an X.
They have prime factorization.
Because they have a prime factorization, namely just themselves.
And then you can break up every not prime into
Well, that's what we're trying to prove now. But we got those ones for free. No, you can't just say that. You're trying to use this theorem to prove the theorem. Because you're assuming that every integer can be broken up into its prime factors. That's what we're showing. So we know that 1 can, because it's an empty product. And we know that any prime can, because it's just the prime itself. So those are the only ones we know so far. So we for sure know that 1's not in X, and we for sure know that no prime P is in X. Assume by way of contradiction that X is not empty. We know X really is empty. We're doing proof by contradiction. Assume by way of contradiction that X is not empty, and so it has a least element. And so let little x be its least element.
Okay.
Now I know that 1 isn't in here, so whatever this x is, it has to be greater than 1.
Yes.
And whatever the x is, it also has to not be prime.
True.
And we already proved that every positive integer greater than 1 that's not prime is composite.
True.
So now x has to be composite.
Yep.
With me so far? So, since it's composite, what does that mean? Going back to our definition of composite. If a number is composite, that means that there exist integers a and b such that a and b are between 1 and x, and a times b equals x.
Yeah.
Or in high-level language, what does it mean for a number to be composite? You can break it up into 2 smaller numbers that aren't 1.
Yeah.
12 is composite because you can break it up into 3 and 4. 60 is composite because you can break it up into 5 and 12. 47 is prime. You can't break it up into 2 smaller numbers. You can only break it up into 47 and 1. All right. So x is greater than 1. X isn't prime, therefore it has to be composite. Therefore, there's an a and b between 1 and x such that their product equals x. Now, since a is less than x, and x was a small c without a prime factorization, a must have a prime factorization. And since b is smaller than x, and x was the smallest number without a prime factorization, b must have a prime factorization. So a and b both have a prime factorization. And when you multiply them together, you get x. So x has a prime factorization. Contradiction. X was the smallest number without a prime factorization. We could break x up into a and b. A and b both have prime factorizations. Multiply those together, you get x's prime factorization.
So x is not an x.
So x is not an x.
And
Exactly.
every least element is not an x, so therefore it's empty.
Therefore, x is empty, and therefore they don't have it. That's exactly what we're going to say.
Why is there so many more?
Because now we got to prove it's unique.
Okay.
So, since a is less than x and b is less than x, they have prime factorizations. We'll say a is equal to the product of m primes, whatever they are, p1 times p2 times whatever. And b is equal to the product of q1 times q2 times all the way to q sub l, whatever. So then x is equal to its prime factorization, or a's prime factorization times b's prime factorization. So x has a prime factorization. Contradiction. Therefore, every positive integer has a prime factorization. That's what we've shown so far. Now we need to show it's unique. So now, next, we're going to let y be the set of all the positive integers that have 2 or more unique prime factorizations.
And we're showing you y is empty.
And we're going to show that y is empty. Exactly. So assume by way of contradiction that y is not empty, and so has a least element, call it little y. Then little y can be expressed as 2 unique prime factorizations. Y can be expressed as 2 unique prime factorizations. So y can be represented as a prime p1 times p2 times ... all the way up to p sub t. We all know how many.
Okay.
Could be something like 2 times 5 times 41. I don't know. And it also has another prime factorization. q1 times q2 ... times qs. Where the p's and q's have no common elements. In other words, if 2 shows up here, 2 cannot also show up here. How do I know that?
Because they're different. They're unique.
Well, maybe they're different total, but why can't they still both have a 2? Maybe this is a 235 and this is a 241. Why can't they have a 2 in both of them? Because if I could have a 2 in both of them, take the 2 out of both of those, we still have the same numbers and we get a smaller y. Y is the smallest element that has 2 unique prime factorizations.
Okay.
So there can't be a common prime in either of these. Because if there were, we could get a smaller y by getting rid of that common prime. Okay, so where the p's and q's have no common element, otherwise removing the common element gives us a smaller y. All right, so then what do I know? So then I know this prime factorization is equal to this prime factorization, where none of these primes are the same as any of these primes. right?
Yes.
Okay. Now, if this whole product is equal to Q, just put parentheses right here. P1 times something is equal to some product of Q's.
Okay.
Or in other words, P1 divides that product of Q's.
Okay.
Or in other words, P1 is equal to one of those Q's.
Yep.
Contradiction. Because that means P's and Q's have a common element.
Okay.
Contradiction. Therefore, every n in Z plus has a unique prime factorization.
Yes.
Alright. It's really not that bad of a proof.
It's not that bad.
It's a little bit wordy. I feel like the one we did earlier today was the hardest one we did today. Maybe the proof by induction one, you guys still don't like induction. I don't know. Alright. Now we're just going to do some just for fun proofs. These aren't really pertinent to the material. So, just for fun proofs. Now let's prove that there's an infinite number of primes. This is one that Euclid proved way back in the day. Let's prove that there's an infinite number of primes. Assume by way of contradiction that there are only finitely many primes. And if there's only finitely many primes, then there's a biggest prime number, right?
Yeah.
Take a finite numbers, pick the biggest out of them, that's our biggest number. So assume by way of contradiction that there are finitely many prime numbers, and let P be the biggest of them.
Okay.
Alright, now we're going to construct some new number, call it little n. N is going to equal 2 times 3 times 5 times 7 times 11 times 13 all the way up to P, up to the biggest prime, whatever that is.
Okay.
So it's going to equal that whole product plus 1. You with me?
Sure. What?
And now n is going to be prime. How do I know n is prime? When I divide by 2, I get a remainder of 1. So 2 doesn't go into it evenly. When I divide by 3, I get a remainder of 1. So 3 doesn't go into it evenly. When I divide by 5, I get a remainder of 1.
What are you dividing from? Where's the division?
What are you dividing?
Oh, n is equal to, write bigger here. N is equal to 2 times 3 times 5 times ... N is equal to the product of every prime number plus 1.
You just letting it do that. Okay.
That's our definition for n.
Okay.
This is the way you can always generate a new prime number, by the way. Once you get one prime number, you can generate infinitely many following this pattern.
Okay.
It won't give you every prime number, but it gives you infinitely many. But either way. So now look at n. N is equal to this thing, right?
Yep.
Now let's see, is n divisible by 2?
No.
No. Because when we divide by 2, we're going to have a remainder of 1. Because n is equal to 2 times this integer plus 1.
Okay.
When I take n and I divide it by 3,
Remainder 1.
we get a remainder 1. When I divide by 5,
Remainder 1.
when I divide by 7,
Remainder 1.
when I divide by p.
Remainder 1.
But it has to have a unique prime factorization. So what are the primes that go into it?
All those.
2 didn't, 3 didn't, 5 didn't, 7 didn't.
So.
The only thing that goes into it is itself, n.
And 1.
And 1. 1 goes into it. But 1's not prime.
Okay, yeah.
So the only prime factor it can possibly have is itself. Because none of these primes divide it. Therefore, there's an infinitely many number of primes. And so this is the way that you can always generate new primes. I can start with just 2. I know that's prime. So 2 plus 1 is also prime, which is equal to 3.
And 3 plus 1 is also prime.
Not 3 plus 1.
Yeah.
So now I say, now I know 2 and 3 are prime, so 2 times 3 plus 1 is a prime.
7.
Which gives me 7. Okay, now I know 2, 3, and 7. So now I know 2 times 3 times 7 plus 1 is prime.
4, 3. And this
It's
13.
11.
It doesn't get all of them.
Okay.
Oh, no, it doesn't.
It doesn't get all of them, but you can follow this pattern forever and get infinitely many of them.
53.
So following this pattern forever, you can generate as many primes as you want. So there's infinitely many primes.
It is 11.
Now let's do one of the coolest proofs I know for the square root of 2 is irrational.
Okay.
And we can do a really simple proof of this. If some of you have seen me do this before, it's kind of a messy, you gotta do a little bit of hand waving type proof. With the fundamental theorem of arithmetic, we could prove it very directly, very easily. So 1, assume by way of contradiction
Mr. Eva, okay.
that the square root of 2 is rational.
It's not.
Huh? Well, what does that mean? That means that there exist integers a and b
Square root 2 equals
such that a over b is equal to the square root of 2. That's what it means to be rational, is you can express as a fraction, right?
Yep, right.
So now, if I know that a over b is equal to 2, if I square both sides, I know that a squared over b squared is equal to 2.
Yes.
Just squared both sides. You with me?
Okay.
So now I know that a squared is equal to 2 times b squared.
Okay.
Now, maybe I'll just start from here. The logic is easy, but it might get a little bit wordy. When we do the prime factorization of a,
It's A and A.
no, it's prime factorization. A could be some number. A could be 1,596. We don't know what a is. But it has a unique prime factorization. A does. Right? Think about how many times 2 shows up in A. 2 either shows up 0 times, or 1 time, or 2 times, or 3 times, or 4 times, or 5 times, or 6 times, whatever. When we do its whole prime factorization. For example, if A here happened to be,
748.
well, we'll just say 64. What's the prime factorization of 64?
2, 2, 2, 2, 2, 2, 2, 2.
We could do 8 and 8,
Which is 4 twos.
which is 2 and 4, 2 and 4, which is 2 and 2, 2 and 2, and so it's 2 6 times. So whatever our A is, it has some number of 2's. You with me? We'll say it has k2's just to write a number here. Then if I take A and I square it, how many 2's does it have?
More than that.
K.
Twice as many.
Yeah.
So A is going to have 2 k2's. You with me? Now B here has some number of 2's as well. How many 2's does it have? It has m of them.
Okay.
Some number. 0, 1, 2, 3, I don't know. Some number of them. So B squared has 2n 2's
Yep.
in its prime
It
factorization.
has 4 MTUs.
So over here we have 2k 2's. Over here we have 2m 2's plus 1.
Plus 1.
So we get an even number of 2's equaling an odd number of 2's. Contradiction. An even's never equal to an odd.
Weird.
Because they have to have the same number of 2's on both sides because they have the same unique prime factorization.
Yeah.
So however many times 2 shows up over here, it has to show up over here. But 2 always shows up here an even number of times. 2 always shows up here an odd number of times. Contradiction. So 2 has to show up on this 2 has to show up on either side the same number of times. It shows up here an even number of times, here an odd number of times. Therefore, square root 2 is irrational.
Yeah.
And the author gives a couple more proofs at the end of this chapter, or at the end of the section, showing that the square root 2 is irrational. This one's my personal favorite for showing that the square root 2 is irrational.
Or just use a calculator, but you know.
Well, the calculator never can give you an irrational number. That is an impossible thing for a calculator to do.
Yeah.
Because it always has to do some approximation. So no, your calculator always spits out rational. And so it spits out some number that's really, 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 really close to the square root of 2. But it does not spit out the square root of 2. It can't. There's no way for it to do that. So no, just using your calculator doesn't answer the question.
That doesn't.
It's the difference in thinking like a Babylonian versus thinking like a Greek. The Babylonian says, here's the square root of 2. And the Greek says, is that just really, really close, or is that actually what it is? They said, who cares? It's close enough. And the Greeks got to work. They found out, actually, you can't write it as a number, but they call it a number. And so the Babylonians just had the approximation. Okay, that's the end of that chapter. And we got through it all, so you guys can go on break, and we got a test next week, and you can ask me any homework questions.
No, we don't.
Oh my God.
You do. We finished it.
No, we